I'm Junichiro Horikawa, and thank you for attending my presentation, Digital Fabrication with Houdini at Houdini HIVE, SIGGRAPH. Okay, so let me briefly introduce myself. I am a freelance designer and CEO of Orange Jellies, which is a self-employed company. I also work as a project researcher at currently Kyoto Institute of Technologies at Kyoto, as well as in Tokyo University. And additionally, I'm currently a partner of a design team called SIGGRAPH. And another partner is Hiromasa Fukaji, is a graphic designer. We're making, based on the procedural designs, to make it a graphic or product design as a team. Okay. And I am currently working in various fields such as architecture, graphic design, fashion, and product design. And recently, Houdini, in this few years, the Houdini plays a crucial role in all these fields for my work. And recently, I have several opportunities to use Houdini in the context of digital fabrication. So today, I'd like to share how I leverage Houdini in various fields for this digital fabrication. Now, digital fabrication bridges the gap between the virtual data made in virtual programs like Houdini and to a physical objects. So examples of this process include such as 3D printing, laser cutting, and CNC milling. And of course, there are much more output you can do with bridging between the virtual data and physical objects. Now, general workflow of my digital fabrication process involves three main steps. One, first of all, you create your digital design, either 2D or 3D, in any software, in this case, in Houdini. And next, you refine or generate variations using procedural method, in my case, and which is in many cases optional. And finally, you prepare a manufacturing data for the machine to output the physical object, such as G-code for 3D printers and so on, for machines to fabricate the physical object. Now, Houdini actually excels in this workflow because it can handle every step seamlessly. Its procedural capabilities make it a powerful tool for generating design, ensuring manufacturability if you code it by yourself, and even directly creating machine-readable data with functions prepared in Houdini. So today, I would like to present four specific examples of how Houdini can be used in digital fabrication in this step, in this manner. So first, I would like to talk about 3D printable modeling using Houdini, as well as molding simulations. And the third one is a bit off the grid, off the topic of digital fabrication, but I also would like to talk about using Houdini for cloth simulations for physical fashion designs. And the last, I would like to talk about how you can use the Houdini to directly generate manufacturing data. So let's start by talking about the 3D printable modeling. One of the key ways Houdini can be used in digital fabrication. And when we talk about 3D printable modeling, we're not just referring to creating a 3D object, but any 3D modeling software can make virtual objects, but ensuring those objects are 3D printable using 3D printers requires meeting specific criteria. For example, let's consider combining three randomly rotated boxes like this one, like a simple object, into one shape, one 3D printable shape. If these boxes intersect internally and you try to print the object, the intersecting planes in internal geometry will cause errors. For 3D printing, the object must meet two key requirements. One is it must be a solid object without internal intersections or self-intersections. So if you have things like the left one, if you clip the objects and if you see intersections inside, then that's going to cause you some errors when you do a printing. And it must be a watertight, meaning there are no gaps or holes in the geometry. So you have to have the solid and watertight geometry in order to be able to print. To address these challenges in Houdini, I mean, it's a simple issues, a problem. But one way to solve this problem in Houdini is to use, of course, a Boolean union. This is a common feature in 3D modeling. Any 3D modeling software that combines multiple solids effectively, multiple solids into a single watertight object. It's simple and effective for most of the cases. However, a Boolean operations can be computationally intensive if you have tons of massive amount of objects, or having some complex intersections like having the same planes being touched together. So they may have a chance to fail when dealing with intersecting planes on the same level sometimes. Another way to solve this issue is using a VDV operations, an alternative and often more reliable approach. Thank you. In Houdini, VDV represents objects as voxel-based volumes rather than polygons, allowing for robust operations like merging and union. With the VDV from polygon node, you can convert polygonal geometry into a VDV volume, perform a union operation to combine objects, and then convert it back to polygon. And as a result, you get a watertight geometry. The advantage of VDV is its reliability, I think. It guarantees a solid, watertight objects, even for really complex shape. However, there are downsides as well. You need to specify resolutions for the VDV operations, and if the resolution is too low, the edges of the hard geometry object may become slightly rounded. So despite this, the method is highly effective for ensuring 3D printability. So most of the cases when I do 3D printing, I use VDV operations on most of the objects. So let me give you an example, some detailed examples how I use VDV method in a real object, real digital fabricated object. A few years ago, the Takaoka Craft Hackathon was held in Japan, Takaoka, which is the area where craftsmen are working, metal craftsmen are working. Me and the team of craftsmen and some AI researchers did the design using a 3D printing to create a tea vase. Tea vessels or tea vase. And the process began by creating a vase shape for the vase and then adding intricate slime mold inspired branching networks using so-called space colony algorithms. By using the VDV workflow, I ensured the final design was both complex and perfectly suited for 3D printing. Now, let me walk you through the process, briefly walk you through the process I used for this project in Houdini. First, I started by creating a vase shape for the vase or cup, designed to be used for the tea ceremony. After that, I scattered points around the base objects like this, and based on those points, these points served as a seed for the slime mold network using space colonization algorithm. The key idea here was to start from a single point to generate a network wrapping around the vase object using the solver. The goal was to create a pipe-like, afterwards, the goal was to create a pipe-like structure derived from the mold simulations like this one. So initially, this network was visualized as curve like this. But for the final objects, we wanted to have it as a physical object, 3D printed. So what we did is what we wanted to have is to attempt create a thickness to those curves. Well, first I attempted to use the polywire method to generate a pipe network, but it didn't yield clean result because of the many intersections of the wires, and it was pretty messy. So to overcome this, I used the node BDV from particles. So I converted the points on a curve into BDV spheres, and then combine all these spheres together to make it look like a pipe shape. This approach involved placing small spheres at each points, and the result looks like this. Next, I created a BDV version of the base shape, and then merged it into merge two volumes together using BDV combine node with the SDF union option. Okay. Once the merging was complete, the union was complete, then I converted back to a polygon so that I'll be able to print it in a 3D printable machines. And I also made sure that everything is connected. You see some virtual objects floating around. I just deleted all those floating objects and make sure everything is in one shape. Okay. And since the object was not intended to be a final 3D print itself, I mean, actually, what we did is to use this for a mold object for the wax, mold object for the casting metal, the metal. So we wanted to first print this with a wax shape and then later cast a metal to it. So there are some constraints when you do that. You need to have at least 1 to 2 millimeter thickness to each branch. So I had to make sure that each branch has this thickness and everything is also connected. And you can see some simulations, what I did here. How do I play it? What do I see? It's just the virtual simulations I did to create a bunch of designs using different properties or different parameters. This is just a test to see which one looks best in the final physical object. And we did the test printing with a bunch of parameters like this, and in the end we have decided what we think is the best for the final metal casting. So for the process for the metal casting, what we did is to use a SLA type 3D printer using wax material. And wax was chosen because it allows for high precise printing and can be directly used as a casting mold. And once the wax object was printed, we constructed a casting tree. This image is not really related to our product, but just to show the process. Okay, this tree made entirely of wax, including the object itself, served as a channel system for pouring the molten metal. And using a technique called precision casting technique, we pour the metal into the wax mold. Then finally, after the casting process was complete, we have taken out the cast metal and polished the object to achieve the desired final design and aesthetic for the physical object. And this is the final result we got as a physical object. The design was really a complex shape for a actual 3D printable objects, but if you have just used the Boolean union, just like in other softwares, but that might going to fail because of all those intersections between the vase and the networks and all those like thing branches. And so I think it was difficult to achieve without VDV functions available in Houdini in this case. So that's one of the example you could use, which I use a lot when I do 3D printing projects in Houdini. A simple technique, but pretty useful. Yes. Okay, let's go to the second examples. So quite similar to the previous project, but the second example I'd like to share is about simulating the molding. Previously, I showed you the direct casting to the 3D printed objects, but in this case, what I'd like to show you is the simulating the actual mold. So to get you the brief idea, the molding is a fabrication method used to create objects like cast metals, porcelain, or ceramics. It works by forming an empty space into which material is poured or pressed. The material, which is initially soft, is going to be hardens through the process like heating or cooling, results in a solid object. Well, once the material hardens, the object must be removed from the mold. This often involves splitting the mold into at least two separate pieces. To ensure this process works smoothly, the geometry of the object must allow for clean removal with minimum friction so that the object's not going to break. This usually means designing the mold so it separates along one or two clear directions, and sometimes more. And though complex design may require more, And I think, in my experience, Houdini is also an excellent tool for analyzing and optimizing objects for the molding. It helps determine whether an object's geometry is suitable for molding and identifies the best directions for removing the objects from the mold. Here's some simple examples I created in Houdini to assess whether an object is moldable. So first, let's say you have just a sphere objects, and I calculate the dot product between the normal direction of the sphere, each point on the sphere, and the directions that I want to use for the molding. And this, as a output, as a result of the dot product, this gives you a measurement of how well each surface aligns with the removal direction. Like this. So what I'm doing is just visualizing the dot product value. So the yellowish color determines the value which is more than 0, and the bluish colors determines the value, the dot product value is less than 0. So negative value and positive value. So what we can see is that the positive value, if you have the big island of a positive value, then that ensures that you are able to use it as a mold. You can pull out the mold shape. So from this visualization, I could identify the line, also the seam line, where the mold should split, which is on the center. In a clean split, red and yellow areas on the one side align with the blue areas on the other. So without isolated regions, this indicates the objects is suitable for molding. However, if you try this method in complex geometries like this one, with features like valleys or overhangs can cause some problems. For example, currently in the image, the black shaded regions in my test reveals shadowed areas that cannot be seen from the direction of the mold. That these areas are impossible to mold because without significant modifications. If you're trying to pull it from that directions, if you have any shadows, then you're not going to be able to use it. You're not going to be able to make that part, the hidden part. So the key takeaway here is that if any part of the object is hidden from intended mold directions, it cannot be cleanly removed. For detail or intricate objects, analysis like this is essential to ensure moldability. Also, for successful molding, even if an object surface is facing directly towards the mold, removal directions issued could still arise if the top and the bottom or side edges of the objects are perpendicular to the molding directions. This perpendicular alignment can create significant frictions, which when attempting to remove the object from the mold. So to avoid this, it's a good practice to introduce slight tapers or angled surfaces, like on the right-hand side. These angles reduce frictions and make it much easier to remove the objects cleanly from the mold. And I would like to show some detailed examples using this technique. We applied this technique in a project called Compote, which I also have the real physical objects here. So if anybody is interested, maybe after the presentation come down and take a look. This project done with a collaboration with Fukaji Hiromasa, a designer and a graphic researcher on the SIGGRAPH. The goal was to create a ceramic flower pot with a unique appearance, which is impossible to be made just by hand. So let me just explain how I created this shape, first of all. So procedurally, I started by creating an egg-shaped base like this one. Then inside the shape, I distributed points to generate 3D Voronoi structures. Then take out the external cells to give a rock-like shape like these, and combine with the cylindrical top sections for the functional as a teapot, to make it function as a teapot. So once the base geometry was created, I also converted the entire model into a volume representation and then turn it into a voxel-based geometry. This gave the object a blocky, almost Minecraft-like appearance, which is this one. You can also take a look at this one later. After that, I converted the voxel-based geometry back into a smooth polygonal shape. Now, at this stage, Fukaji, the designer, brought his own refinements into the process. Using Rhino, he further developed the design and imported back into Houdini to finalize the geometry. So, well, initially I wanted to done everything in Houdini, but in order to be able to collaborate with the designer, in the end, Fukaji wanted to use his own model. So I also created this path in order to be able to import custom objects to Houdini to convert it into a voxel shape as well. And it would have been better if the design feedback was done on Houdini. But as you all know, Houdini is really powerful, but not really an intuitive tool for anyone, to use. So I'm still seeking for the best practice for design collaborations, especially people who doesn't have any idea about using complex softwares. I'm not meaning to say Houdini is complex, but try to make it more intuitive. So after finalizing the geometry, I analyzed the design in Houdini to check whether it was suitable for molding using the technique that I show you to analyze the geometry. And the key aspect of this is this analysis was determine the best seam line for the splitting the mold. I used the simple functions to evaluate whether the mold removal directions were appropriate for the design. From this analysis, we found that keeping the mold seam line as straight as possible was the most effective solution when you actually create a physical mold object. So as a result, the final object was designed to be symmetrical in the end, so that you'll have a promising straight lines on the middle, which made creating and using the mold much easier. So while we experimented with different seamline placements, asymmetrical designs made the molding process significantly more complex. So this choice to prioritize symmetry was aligned with physical molding limitations and practical considerations. And then we do the same analysis for the converted voxel shape to make sure that everything is okay. And once we have this voxel shape, what we need to do next is to make sure there are no hard frictions on the mold directions. So we needed to assign some tapers to each of the planes, which is on the top and the side, perpendicular to the mold directions. These tapers reduce the frictions, making it easier to remove the final ceramic objects from the mold. And this step was pretty critical in short to smooth and efficient molding process, which was all calculated in Vex and wasn't that simple to do. Now, this is the final preview for the 3D shape and the mold shape. The mold shape should look like this. Well, after preparing the geometry, I tested the mold design by simulating different molding directions, like having, if it's possible to have multiple directions in Houdini. Well, system-wise, it was possible, but when it comes to actually use it in a physical space, having multiple directions is really hard to really do it in physical space. So we have tried from the two directions in this examples. And this step, from now on, I'm going to show you how physically it's been created. So the next step involved creating physical mold and casting off the object. First, we finalized the geometry and 3D printed using SLA printer. In this case, we're just using the normal resin material, which provided a high level of precision. Then we have put the 3D printed objects on a vase like this one and pour in a plaster, melted plaster over it to create a mold. Once the plaster hardened, it becomes a reusable mold for casting like this. Then we have poured the softened clay into the plaster mold like this. This clay formed the shape of the flower pot, leaving an empty space at the base for their functionality. After the clay hardened, the object was carefully removed from the plaster mold and fired into electrical kiln at the approximately 800 degrees Celsius. And these steps transformed the clay into an unglazed ceramic piece. Next, the ceramic piece was sprayed with the glaze to add a finished look. And then we fired a second time in the kiln, approximately 1,200 Celsius degrees, completing the process. And the final ceramic flower pot was detailed, had a detailed rock-like textures as intended. So the things that I wanted to show here was how I use Houdini to simulate the molding process, which looks pretty simple, but really an important process. These objects are also available online, so if you're interested, maybe search for it. Okay, the next example, I would like to share about the detailed cloth simulations using Houdini for digital fabrication. Now, this case is a bit slightly different because the focus is using virtual designs as a feedback for creating real physical cloth. Recently, some of the clothes are made directly from virtual data, like whole garment from Shimaseki, or digital weaving machine with jacquard system that can be called as a part of digital fabrication. And my personal goal is to create a data for such machines. But before that, I wanted to create a visual simulations which can be feedback to the design process of fashion, which is usually done in 2D in fashion design field. Specifically, I wanted to simulate the detailed three-dimensional textures of textiles, such as like complex patterns like Canadian smocking or pleats, like these. And actually, there are tools available specifically for simulating cloth behaviors, such as Cloth 3D. This tool allows designers to simulate how fabric behaves in the real world, incorporating physical properties of different materials and body shapes. Many might ask, so why not just use Cloth 3D for this instead of Houdini? Well, the answer lies in the level of detail and control. While Cloth 3D is excellent for simulating overall cloth structures and transforming 2D layouts into the fine 3D garments, but it lacks precisions when it comes to creating fine details such as pleats or complex patterns like Canadian smocking, just as I show like this one. So I think this is where Houdini excels. Its procedural workflow makes it possible to simulate these intricate details algorithmically. So my goal was to create controlled wrinkles and shrinkage effects on the clothes to replicate real-world behavior while maintaining feedback accuracy between the virtual design and physical object. So I wanted to simulate how threads within the cloth could shrink to create patterns and wrinkles. To demonstrate this, imagine a plane representing the fabric. On the left-hand side, you see the grid of the plane symbolizing the base cloth. On the right-hand side, there are threads running through the cloth. These threads are designed to shrink, and objective is to see how the shrinking affect the fabric shape. Now, using Houdini, this was pretty straightforward to simulate if you know how to use Vellum. I set up a custom constraints in the Vellum solver, specifically using stitch constraints or sometimes glue constraints to define the threads, endpoints, and control their shrinkage. Similar result could be done maybe in distance constraints as well. The resulting simulations showcased how the thread's shrinkage caused the cloth to wrinkle and form patterns, achieving the desired effect, like this one. So one practical application of this method was done in a research project called Zero Waste Nishijin Textile. This project aimed to design clothes using Nishijin weaving from Kyoto while adhering a zero waste concept. Zero waste in this context means using the entire square piece of fabric for the design without generating any material waste. So the research was led by textile designer and researcher Kaori Ueda from Kyoto Saga University, as well as Vina Ross, a tutor and researcher in textile research at RCA. Together, they integrated the shrinking properties of strong twist yarn into the traditional Nishijin weaving technique. The cloth design incorporated both horizontal and vertical strong twist yarn to create controlled wrinkles patterns for example, the middle sections of fabric shrinks significantly, and where the red line is, and while the top and bottom remains relatively unshrunken, where the shrinking distance is small. And it's pretty hard to simulate things like this in Cloth 3D because you cannot customly create a constraints like this one. So this I thought where Houdini excels. As a sample project, we simulated this concept for simple jacket design. Here's how it's done. The 2D layout of fabric pattern was first created in Illustrator by a researcher with a guide where you should implement the shrinkage with strong twist yarn, which is these square patterns. And this was imported into Houdini and converted into curved data for further processing. Once the curves were imported, I generated a meshed surface with a sufficient resolutions so that I can have enough mesh for the wrinkles. Additionally, I designed specific areas for the fabric to remain unchanged by implementing square-shaped regions. These static areas provide contrast to the sections influenced by shrinking threads. Small threads, horizontal small threads are added to the fabric surface in area design to shrink. These threads were assigned shrinkage properties using glue constraints to enable the simulations to show how the clothes would respond to the shrinking forces. I have specifically used vellum constraints node with the glue option. So using the drape and also using the vellum drape node, I combine all these elements together, the non-shrinking square regions and shrinking threads into a single simulations. The resulting simulations show the clear difference in tension across the cloth. So you can see it on the middle part. Sections of fabric, there are shrinking threads where it's concentrated, tightened significantly. This created a dense patterns on wrinkles compared to the top and bottom parts, which remained relatively loose and unshrunken. You can also see the localized areas where the fabric became particularly tight, forming intricate patterns. These results provided valuable insights into how the clothes could behave during actual fabrication. Now, these simulations focused solely on horizontal shrinkage, which in the left-hand side, it also has vertical shrinkage as well, which is why the final result did not perfectly replicate the physical output. However, the primary intention was to test whether Houdini could be used to simulate such interactions and provide reliable feedback for the physical designs. In this regard, the project was successful. It demonstrated that the Houdini could effectively simulate shrinkage patterns and inform physical production moving forward. And we plan to expand this method to accommodate more complex design and multi-directional shrinkage effects. Okay, so I'm gonna make it faster. The final examples I wanna share is about generating manufacturing data using Houdini. So this example demonstrates how Houdini can be used to create the actual instructions needed to operate digital fabrication machines like 3D printers and so on. So to fabricate physical object, the process typically starts with the digital design, then design must be converted into manufacturing data, then using machines to actually output the physical object. For example, for the middle part, design data for 3D printing, you use STL, CNC machines, it might be step files and so on. But in the end, in the machine, at the core of many of these processes, universal control language, such as G-code. If the machine is moving a nozzle like the right-hand side one, most of the time you could use this format called G-code. G-code is essentially a series of instructions that tells the machine where to move, how fast to move, and how much material to deposit or cut. For example, in 3D printing, G-code specify nozzle positions, as well as speed and material discharge volume. Now, by generating G-code directly in Houdini, you can have more flexibility and control over the fabrication process instead of relying on like slicer, like Cura, coming with a 3D printer, which will generate your G-code automatically using your STL model, But if you could generate your own G code, then you could have more control over the printing machines. For instance, consider spiral polyline design like this one. Each point on the polyline contains information about its position, speed, and material discharge. By combining these points information into lines of G code, you can already create a custom shapes ready for fabrication by 3D printing. So the method is pretty simple. So I recently conducted a workshop at Kyoto Institute of Technology, and I would like to show how I use this method generating G code in this workshop. This workshop collaborated with Yuko Ishizu, a geometry engineer at GEL. The workshop focused on creating clay 3D printed objects using Houdini to directly generate G code. So the workshop was designed to be accessible, allowing anyone to include students to participate at low cost. And at the end of the process, and create G code for clay 3D printers for practice. At the end of the process, participants were able to output their physical ceramic objects by baking them in an electric kiln available at the university. And Houdini file used in the workshop was developed by Yuko Ishizu in this case. I have just advised her to how data can be organized. It included all the necessary designs and output options like designing, converting the 3D data into G code, and export the G code as a text file so that the machine can read it. And I'll just go through the process quickly. So we have the base shape. The Houdini file gives you options to change the patterns on the surface and be able to create a contour curve. And what's important here is that you have to make sure that the order of the curve is also based on the order of the machine, how the machine moves. So we made sure the order is going from bottom to top. And this shows the image we also made some simple visual simulations to see how the machine should move. And if everything looks good, we also calculate how much materials we're going to use by applying the thickness to the curve, see what's the size of the shape and how much material is going to use, how much clay you're going to use. Once you have these analysis, we have converted the curve data into a G code by applying the position of each point as X and Y and Z direct coordinates, as well as speed and amount of volume clay should be extracted based on the whole material size. And we have used 5 different machines, which is kind of crazy because everything needs to be set up in different method. And we put this clay into the machines like this, printed, and using the similar kiln we used in this pot design. And we also made a workshop to create a manual glazing. And in the end, we have a tea party and cafe by using everybody's final output, using as a base for the sweets. And that's what we had in the final result. So these are the final piece made by the participants of the workshop. Everything looks pretty cool. I mean, some people wanted to try the custom shape, so we specifically helped with them as well. So as a conclusion, Houdini is often seen as a tool for virtual spaces, I think, but these examples highlights its potential for creating physical objects as well, from designing to generating manufacturing data and producing real-world outputs. Houdini, I think, proves to be a versatile tool. So I hope this inspires more people to explore Houdini as a medium for outputting physical objects and integrating design feedback into their workflow. Even for a hobby, it should be really fun. And that's it. Thank you.